LearningMeasure.tv, a science and engineering podcast with emphasis on measurement, brought to you by David Archer and LearningMeasure.com.
Episode 40, S parameters.
Hello, I'm David Archer. I'm owner of LearningMeasure.com and LearningMeasure.tv. LearningMeasure.com is a subscription-based training website where when you register as a student, you get 1 week free, and after that it's $5 a month for access to all the courses there. I'd like to announce the addition of the following courses to the course catalog. C-Prog 101, Introduction to the C Programming Language. Many of you actually, surprisingly to me, asked for a C programming language course to be put on the website. I guess because a lot of programming is done in measurement, and that is true. When you get involved in measurement, you do a lot of automation, although you would sometimes use LabVIEW or some other thing, Agilent V or something. Instrument 404, Amplifier Types and Specifications, which is basically what it sounds like. It talks about the various types of amplifiers and amplifier specifications. And Measurement 462, Introduction to Mil Standard 461 CS Measurements. That's a third in a series of 4 courses that we're putting together on Mil Standard 461 testing. The topic I wanted to talk about today in today's podcast is S parameters. Now, S parameters are used basically by RF engineer types to describe networks. And it was a concept that was basically borrowed from particle physics and by the engineers. And so let's say we have this abstract network. We're just draw as a blob. And there's these input ports. So there's an in and an out at each of these ports. So these ports are labeled 1. You know, some comes in and out of all these ports. And so you have all this network of whatever it could be. It could be some sort of circuit. It could be a cell phone network. It could be all kinds of stuff. And let's say you inject, all these ports are labeled 1, 2, N, M, you know, so that there's N ports in there. Well, let's say it's N ports. N is the number of ports. Well, let's say you inject a signal into port N with a wave amplitude, which we'll define later maybe as A1. And at port M, what comes out is a wave amplitude of B1, assuming all the other ports are terminated so there's nothing going in or out. One can define then SMN, S parameter, as the ratio of the wave coming out at port M to the input at port N. So the SMN is you stimulate that port N and you measure at port M. So the first number tells what's coming out. Second number is where it's going in. So and these things here, this ratio, these things are like voltages. Their square is proportional to power. So this is basically a voltage ratio. So for the generalized N port, you can have this SMN. Well, what does that mean? Or what does that mean in? Let's start with the simplest case of all, a one-port device. One-port device might be something like a termination, a load, something like that. So you have one port. You got a goes into and it goes out to, and you have whatever it is. Now, generally, the way that we draw these things is not like that. What we generally do is we'll draw it like this. We have something coming in, A1, Then we draw a little arrow saying which way it would go, and then something coming out, B1. So S11 equals, like I said, B1 over A1. Okay, so that's a voltage ratio. This is also called the voltage reflection coefficient, which would always, or almost always, is represented by a gamma. You may have also seen another notation. The magnitude of gamma is often referred to as rho, as often indicated with a rho. Now, a Greek letter rho. This is a complex number because not only does the reflected signal have an amplitude, but it has a phase associated. Now, this is all about CW wave type waveform so far. So that's the simplest of all devices. What's the next thing? Well, a two-port device. We just did a one-port device. This is probably the most common thing you'll see, is you draw this with lines and arrows usually. So this is port 1, this is port 2, and this is called a scattering diagram, where this arrow is S12, this is S21, this is S11, and this is S22. Four-port device. So if you had an A1 going, or sorry, yeah, an A1, oh, I got these arrows backwards. No, that was right. So if you have an A1 going in here and a B1 coming out here, or B2 coming out here, S21 equals B2 over A1. If you have an A1 coming out of here and a B1 coming out of here, everything else constant, everything else nothing connected, S11 is B1 over A1, etc. by the definitions. Well, how do you draw these things? You notice I had one arrow upside down. Draw the first one across, second one's got to go the other way. And then these arrows have to be in opposite directions, because otherwise the thing would look like it was going around in circles. This is a scattering diagram for a two-port. Now, what can you do with this? Well, before I get too much farther, let's write this in a different way. One can write B1, if anybody's interested in matrix algebra, we have this. So the S matrix is basically something that relates an input vector to an output vector. Matrix multiplication. So if you have signals both A1 and A2 at a two-port, you're going to have B1 equals S11A1 plus S12 A2. And B2 is S22A2 plus S21 A1. So that's the general case. So if you set, if you take like A2 and set it equal to 0, so you can solve for S11. That's where this came up before. Okay, so if this is, let's say this represents an amplifier. In the case of an amplifier, let's say this is S11 is the input reflection coefficient. Maybe I shouldn't write these out, but S21 is the gain, numeric gain. S12, reverse isolation. And S22, is the output reflection coefficient. Okay, so they have names for amplifiers. A device, a two-port device especially, is called reciprocal. If Sij equals Sji. That's called a reciprocal two-port network. Or in general, for an n-port network, you can have a reciprocal network. Most networks are not reciprocal. In fact, at some level of accuracy, all networks are not reciprocal, but for the most part, for a lot of practical purposes, a lot of devices are reciprocal. Because yeah, if you're going to get down into parts per million, they're not going to be reciprocal for any type of device. But anyway, well, what's the next most complicated thing? We get a one-port and two-port. You'd think it might be a three-port, but no. What happens if you put a one-port on a two-port? So you terminate a two-port device. It now becomes a one-port device, right? So we'll call this gamma, just because we can call it that, to make it separate from the others. So now it's a one-port device. Well, what do you want to know? What you might want to know from this is, what is gamma, let's say, equivalent? What kind of one-port device does this look like? Well, the way this works, and I'll show how these diagrams work, you could go through the matrix stuff, but let's do it this way. Okay, something comes in, right? A1 times S11, something comes in here. B1 gets that. Okay, well, what else? You can follow the path of the things through this. Well, here's a path through the device, this way, and this way. So you add all these up, so this is going to equal to S21 gamma S12 A1. Well, this is also a path through the device. So this is plus S21 S12 gamma S22 gamma, okay, plus there's another path through the device, 1, 2, and out. Well, you can see where this is going. So this ends up being S11. Now if we'll divide by A, B1 over A1, so get the A1 over here. This is S11 plus S21 S12 gamma. Okay, that's in all these terms, right? And then it's going to be 1 plus gamma, or plus S22 gamma plus S22 gamma squared plus, and it turns out, for those of you who understand infinite series, you can sum this series, and you get gamma equivalent, which equals B1 over A1, is equal to S11 plus S21 S12 gamma over 1 minus S22 gamma. This is something that probably should know how to drive if you're going to be in the RF field at all and understand S parameters. This is your basic formula for a two-port cascaded with a one-port, and what it's equivalent, because it only has one parameter now. By putting a load on that end, there's only one parameter. Well, what's the next most complicated thing? Well, let's sort of save that equation somewhere. You can impress your RF engineering friends if you know this. Okay, the next thing is the most complicated thing. Isn't a 3-port yet, it's two 2-ports. So what happens when you put two 2-ports together? Oops. Remember, always draw the arrows so that you can't form loops. I'm not going to, let's call this one S21, and let's call this one S21 prime for the other. And this would be S11 prime, S22 prime. Well, now you can ask other questions like, what's the S11? What are the 4 parameters of this cascaded device? Well, S11, we know how to do that already, because there's only one reflection as far as this thing, so it's basically that same equation. S11 equals, we'll call this double prime, the S parameters for the whole thing, is S11 plus S21, S12, S11 prime over 1 minus S22, S11 prime. Okay, that's the easy one. Looking into this way, S22, exactly the same thing. We know how to do that already. S22 plus S21, S12, S22 over, oh, sorry, prime, these are all prime, 1 minus S22, S11 prime. Well, you can do then the same exercise we did for the 1-port for the 2-port. So that S21 equals, well, there's this path through the device, S21, S12. There's this path through the device, plus S21, S12, S22, S11 prime, plus, you know, then you've got more terms. You've got this path through the device, and then you have this path through the device, and all those paths through the device. You can again sum this, and we get S21 equals S21, S12 over 1 minus S22, S11 prime. So now you know basically what the S parameters of two things cascaded together are. Remember, these are all complex numbers. I'm not going to go to 3 because now the next most complicated thing is a 3-port, but going through all those relationships would take a while. So the two things to remember basically is these two. And then you can handle 1-ports and 2-ports in any RF situation. Now, these reflection coefficients are usually plotted on what's called Smith charts, and that normally what you do for these S21s, they're not looked at directly, but they're looked at in dB. So generally, you look 10 log 10 of S21, and that's like a gain or a loss in dB. Okay, and then so you generally look at the magnitude and phase of the reflection coefficients. You also can look at the magnitude and phase. Oh, actually, I should say magnitude, right? That's generally what you look at. So there's the magnitude and phase of the through parameters. 3-ports get complicated, and I'm not going to do anything this time. I just wanted to sort of introduce these things and do a little series on this, and so we'll talk more about this next time. So This is a little short one, Introduction to S parameters. So if you have any questions about this or anything else, send me an email at questions@learningmeasure.com or learningmeasure.tv. If you have any suggestions for a show or anything else, send me an email at suggestions@learningmeasure.tv. And if you're a vendor that has something to sell, you want to be on our podcast or anything like that, send us an email at vendors@learningmeasure.tv. That's it for this time. Next time I'm hoping to continue on with this S parameter stuff. All right, I'll see you next time.